Okay, so we're going to continue with a second method for proving noise sensitivity. As Christophe already mentioned when he told you an overview of what's coming, he mentioned the first technique was the hypercontractivity, which is the BKS theorem. And he mentioned there'd be a second method related more to computer science. That will be the topic of today's lecture. And then in about 2 lectures will be the third approach, which is a more geometrical approach to the study of the spectrum. So there are things called randomized algorithms in theoretical computer science. And the entire lecture today will be connected to these types of objects. Let me mention that they actually first appeared. So in fact, in the original BKS paper that was already described, Benjamini, Kalai, Schramm, they in fact proved that our basic event, our most important event of percolation crossings, is noise sensitive, actually using randomized algorithms. So in fact, they mentioned in the paper you could sort of do it in the manner that Christophe described, namely you first prove the BKS, and then you compute the influences for percolation. And they mentioned that in the bulk, exactly as Christophe described, that a result of Keston tells us that the influence is at most 1 over n to a power strictly bigger than 1. And then they somehow didn't deal with the boundary issues. They said you probably could do something similar, and rather they used a different approach related to randomized algorithms. I'm not going to describe this approach. I'm just going to make 2 comments about it. It still uses the BKS theorem, the theorem that says if the sum of the squares of the influences goes to 0, then you're noise sensitive. So it still used that. And in the proof, there were basically 2 ingredients. And one of them, the first ingredient, is that monotone functions which are quite independent of majority functions are noise sensitive. So the majority function is stable. So if something's noise sensitive, it's necessarily asymptotically independent of the majority function, because the majority function has its spectral measure on small sets, and a noise sensitive one has it on large sets. So they're necessarily asymptotically independent. It turns out that they prove that if you have a function which is monotone and quite independent of the majority function and all the different types of majority functions, you can take the majority on some subset of the bits. If this happens, then they tend to be noise sensitive. And they prove such a result, And then they used randomized algorithms to show that percolation crossings are fairly independent of majority functions. Okay, this is just a side. I'm not going to go into any details with this approach. And it's, again, the approach. So this is the first appearance of randomized algorithm in noise sensitivity. And the approach uses the BKS theorem. What I'm going to describe to you, the topic of today's lecture, is an approach also which uses randomized algorithms, but you don't need to do any of the hypercontractivity, but rather we'll sort of get a direct link between, we're going to obtain a link between randomized algorithms and the spectrum. So what is a randomized algorithm? So I'm not going to write down the formal definition. I'll do a few words and talk a bit, and then there'll even be an audience participation part of seeing what a randomized algorithm is. And after we're done with that, it should be completely clear what a randomized algorithm is. But in loose terms, it's as follows. So you have a function. So a randomized algorithm for a Boolean function is an algorithm which chooses a bit randomly according to some distribution. Doesn't have to be uniform. It might be degenerate. The algorithm might always choose bit number 2 to begin with. When it chooses that bit, so it chooses a bit randomly according to some distribution, looks at it, and depending on its value, chooses the second bit according randomly according to some distribution. This distribution where you pick the second bit, that's allowed to depend upon the value of the first one you looked at. Maybe you decide to look at the 7th bit, and that was a 1, and you say, since that's a 1, then I'll choose either the 10th bit or the 11th bit at random, maybe 50-50. But had that first bit been a -1, maybe I would have looked over at the first bit. So it's an algorithm that chooses a bit at random according to distribution, looks at it, and depending on its value, chooses the second bit randomly, looks at it, and it just continues. After maybe 13 questions, depending on everything you've seen before, it chooses the 14th bit at random according to some distribution, maybe deterministically, depending on what you've seen so far. And you keep going until you know what the function value is. So at some point, maybe you've looked at 80% of the bits, and you might say, I don't need to know the other bits to know what f is. I already know. For example, if you were looking at a majority function on 101 bits, and you looked at the first 51 bits, and they all happen to have been 1, you would say, I stopped my algorithm. I know the majority is 1. I don't need to look anymore. So that's what a randomized algorithm is. OK. So I want to do 2, both of which have audience participation. So I have a graph on 5 vertices. There are 10 potential edges. For any pair, like 2 and 3, either the edge between them is there or it's not there. So there are 2 choices for each of the 10 edges. So you can think of this as the edges are our bits. They're plus or minus 1, present or absent. And my function is going to be, what I want to know is if the graph is connected. your job is to figure out if this graph is connected, and you're going to ask me different questions about the different edges if they're there. I perhaps should have said it here. Clearly, what you want to do with these randomized algorithms, you could imagine in theoretical computer science, what they want to do is they want to ask very few questions. It costs money to ask questions, and they want to know the answer, the output quickly without asking too many questions. So here, you want to determine whether this graph is connected without asking too many questions. So connectivity corresponds to a Boolean function. You can think of if the graph turns out if the edge configuration, present or not present, if it's connected, the function's 1, and if it's not connected, the function's -1. Okay. So understand algorithm, you'll be the algorithm, so someone yell out for 2 points and to ask me if the edge is there. 1, 2. Good start. 1, 2, that edge is not there, and I denote that by putting a line through it. That edge is not there. 3 and 5. Okay. That edge is not there also. Okay. 1 and 3. 1 and 3. That edge wasn't there either. Next. It's only 10. You got to speed up. Louder, please. 3, 4. 3, 4. That one wasn't there either. I'm sorry? Not yet. What? 3 and 2. 3 and 2 is there. Okay? 2 and 4. 2 and 4 is not there. How many questions have you asked? 1, 2, 3, 4, 5, 6. You have 4 left. You have to do it before the last one. 2 and 5. 2 and 5 is not there. Well, there are 3 left. I don't know if anyone can see the picture. So, can we conclude yet it's connected? It's not? No? I don't think you know yet. There's not too many questions left. 1, 2, 3, 4. How many? What's 1 and 5? 2 and 5 is not there. That was already asked. I should keep track of what's been. What? 3 and. I can't. 2 and 4. 2 and 4. If it's not connected, I made a mistake. Okay. Had I done it correctly, you would have been forced to ask all the questions. So I apologize that this did not work out. If it's true that it's already disconnected. So had I answered the questions properly, in fact, I could have forced you to ask all the questions. It's an interesting minor fact. Now, the point of that was just to tell you, to get a feeling what an algorithm is. You just go by and ask different bits. Now, this was slightly different than the way we should be thinking, because in reality, when we're doing this, the functions are IID coin flips. You might be highly suspicious to the fact that I was giving you IID answers to your questions, and I really wasn't. So you shouldn't think about what I was doing to be a randomized algorithm, but you should, in fact, think of what you were doing, asking questions. So let me do one more.
But why don't you draw the graph that you had in mind?
Are you serious?
Yes, I'm serious.
I didn't have one in mind. Right. Okay. Last thing before we do this. So if we look at 3 majority, the iterated 3 majority function, okay, you recall that I put 0 and 1 bits on the bottom layer. And then the majority of these bits gets placed here, the majority gets placed here, and the majority of these gets placed here. And then I take the majority of these 3 bits and I put it there. And I would want to do this in a way that asks very few questions. So I need 9 IID coin flips. You're 1, 2, 3, 4, 5, 6, 7, 8, 9. All you have to do is generate an IID plus or minus 1 coin flip in your mind independently without flipping, and I ask you what they are. So person 1, okay? Number 4, that's you. Plus or minus 1? Plus, okay? 5, minus. 2, minus. Wait, you're not a... 1, okay? Okay, revenge, okay? Okay, I think you see the point. Yes, you could do it to me too. Okay, so now, enough fun and games. So now hopefully everyone understands what an algorithm is, and now we try to do some mathematics. Okay, so what's important with these algorithms is when you look at the set of bits that you ask about, that will be a random set of the bits. And we denote that by J. So given a randomized algorithm J, A, we let J sub A be the random set of bits probed by the algorithm A. So typically, unlike in the cases we've been happen to have occurred, typically you won't need to ask all the questions. You might get likely and just ask a small percentage and know the answer, and you simply let JA be the random set of the bits which are asked by the algorithm. This is a random set. Now, we want the set to be fairly small. One way to measure that it's small is I could hope that it's very unlikely the first bit is probed. And it's very unlikely the second bit's probed. And maybe it's very unlikely that any fixed bit is probed. So the concept we introduce is called the revealment of our algorithm A. And what it does is it takes the maximum over all the bits, I is the bit, of the probability using the randomized algorithm A that I is in J. This is the probability that the ith bit is asked for by the algorithm, and I take the maximal all the bits. This is the maximal probability that a bit is probed. If we take a simple example, the majority on 3 bits, there's a very simple algorithm I could use in this case. My algorithm A could do is the following. Choose 2 bits at random. So basically, I choose 1 bit at random, and then without even looking at it, I'll just pick the second bit at random. So A chooses 2 bits at random, looks, stops if the same, and of course, if they're not the same, it needs to look at the 3rd bit. Otherwise, looks at the 3rd bit. Yes? Yes. Yes. There are other variants where you might want some approximation, but for today, we want it exactly. The revealment of A, this I will denote by delta sub A. So it's not so hard to compute the revealment for this particular algorithm. Obviously, it's symmetric, so I can just compute that the first bit is revealed. Well, with probability 2/3, it's one of the first 2 bits that you probe. In that case, it will definitely be looked at. So let me just look at the probability 1 is looked at. So this is 2/3, because 2/3 of the times it will be picked right away. And then that one time where you didn't look at it first, there's still a 50-50 chance you'll have to ask what it is. 1/3 times a half. And you end up getting 5/6. So this is this is the revealment for this particular example. You would want to find, we said we want to ask as few questions as possible. You would like this algorithm, you would like to find an algorithm with a very small revealment. So it's natural to define the revealment of F as simply the minimum of delta A over all the possible randomized algorithms for A. So this is the minimum of delta A over all A is a randomized algorithm for your function F. Okay. So it turns out that this thing, which we'll call the revealment of F, is going to be linked up with noise sensitivity in a certain way. And this approach will be able to prove various models are noise sensitive. So let me state the theorem, which I'll call the Revealment Theorem. States the following. Let F be a mapping of, it doesn't have to be we usually think it's a Boolean function, in fact. But in fact, the notion of a revealment makes sense for any function into R. Doesn't have, typically it will be Boolean in the applications, but it could map into R, and you just have to, you keep asking questions until you, until you know what the randomized algorithms are described in the same way. And what we're going to do is the theorem tells us the following. For all k equals 1, 2, 3, the level, the energy, the spectral, the energy layer, the level k spectrum. This was defined as the sum of the Fourier coefficients over S's of size k. This is at most delta F times k times the L2 norm of F squared. So for Boolean functions mapping into 0 into plus minus 1, this term simply disappears. So the point is we're bounding the level k things by this revealment times a factor k. So on the higher level k's, this is extra factor of k. Okay, so this is the inequality that we're going to apply after we prove it. We'll apply it to prove that, for example, percolation crossings are noise sensitive. And it will give a quantitative version for the noise sensitivity of percolation, which will bring the spectrum above a power law. So you'll recall at this stage, based on Christophe's last lecture, we know that most of the spectrum is sitting to the right of some constant times log n, and at most, say for the triangular lattice, n to the 3/4. So this method will bring it above a certain power. It won't be 3/4, but it'll be some positive power. So let me mention a corollary of this. If we have now a sequence of functions fn, and if the revealments approach 0 as n goes to infinity, then Fn is noise sensitive. And this basically follows immediately from this. Proof for every fixed k, if you look at the energy level for our nth function at k, well, we just use this bound. This is delta Fn k times the L2 norm. Oh, these are Boolean. This term disappears. For every fixed k, this, of course, approaches 0 as n goes to infinity. Because this term's going to 0, so for fixed k, this term goes to 0. And we already know from the second lecture of the course that this is exactly equivalent to noise sensitivity, that for any fixed k, the total weight of the Fourier coefficients at level k has to go to 0. And so you immediately get the noise sensitivity. Notice that this implication, here in this theorem, we have the Fourier spectrum coming up. Notice that in this implication, there's no Fourier spectrum mentioned. Both these concepts have nothing to do with spectrum. The revealment is sort of a concept from theoretical computer science. And our conclusion is noise sensitivity, which is more of a probabilistic type of concept rather than Fourier analytic. OK, any questions so far? Yes?
Is there some kind of proof with this theorem
That's a very good question. I have an answer for it, but let me bring it up later. But we'll get to that. OK, so I want to describe a little bit. So I'm going to give you a complete proof of this theorem. But before doing that, I want to describe to it a little bit. So I first want to describe, one, how we think about this, what's going on. And then after that, I want to give you a heuristic, why it's believable, a completely non-rigorous heuristic. And then after that, we'll give a complete proof. So what is happening So our Boolean function, usually we describe it in terms of the majority function, percolation crossings, or iterated majority. But of course, we know the function, in fact, has a Fourier representation. So let's imagine this is the Fourier representation. OK? Here we have a level 1 term, here a level 2, here's a level 3. I doubt very much this is, in fact, a Boolean function. And probably the sum of the coefficients don't add up to 1, unless I was extremely lucky. But just heuristically speaking, this is sort of what our function looks like. OK, now imagine the algorithm asks, say, about the second bit. So maybe bit 2 is probed. And let's say its value is 1. What happens? what happens to our function when bit 2 is probed and its value is 1? So wherever I see in omega 2, I put in a 1. So this term here, this becomes a 1. And are there any, and there's no other, in this particular thing, there's no other omega 2 appearing. But what would happen when I fill, what I do is I just stick in the value. The way I want to represent my function after this information, I've stuck in this bit, and I stick it in wherever the omega 2 appears. So all the monomials which contains a term omega 2 is reduced 1 degree. And this is exactly this is what my new function, basically my new function is. Now maybe the next bit you'll ask might be the 8th bit, and maybe its value will be -1. Well, what happens then? This term here, this disappears, and this becomes minus. What happens over here? This disappears. This becomes a minus. And these two terms canceled. So what can happen is, as you're putting in these bits, certain terms are going to cancel. Maybe, maybe not. Now, after I do this, if there's still true monomials here, other than the constants, if there's still monomials here, but basically this is a Fourier representation of my new function, the function I have based upon fixing all these bits to be what they turned out to be. So if there's still monomials, the function's not constant. I can't possibly know what the function is. Basically, you have to keep on doing this until there's no longer any monomials, until there's only a constant term. And notice is your only hope, there better be cancellation going on. Because if there's no cancellation going on, assuming all your bits appear in the equation, if there's no cancellation, you'll have to ask all the bits and ask all the questions. So the only hope that you'll have of some type of asking fewer questions is having some type of cancellation going on. OK. So that's just maybe to put you in the right mindset. Now let me, yes? I'm sorry, could you say louder, talk louder? I guess we've, not that I'm aware of. I've never thought about trying to do algorithms via looking at this Fourier representation and seeing if they cancel. So it's at least in the examples we know how to find algorithms, that's not the approach. I don't know if that would work or not. I've never thought about it. OK. So let me now, why is it true? So what I'd like to convince you of is just one version of this. Namely, if I look at the first layer Fourier coefficients, this is at most delta. So this is basically going to be the result when k is 1. And gives you some heuristic why this might be believable. OK. So imagine this were false. Imagine delta were very small. But the first weight was something, well, was a half or so. So let me write down the level 1, the Fourier decomposition at level 1. So I have A1 omega 1 plus A2 omega 2 plus A3 omega 3, AN omega n. Now, what I want to do is let's figure out what's going to happen to these terms at the end of the algorithm. At the end of the algorithm, some of these omega 1s and omega 2s, some of them are going to be replaced by plus or minus 1 if they were looked at. And otherwise, if I didn't look at them, they'll remain the same. Since delta is very small, we'll be removing very few of these terms. Since delta is small, maybe I remove this one, and maybe I remove that one. But most of it's going to be there. So most of the weight is still present at the end. OK, now that's not a contradiction. Certainly there can be terms left at the end, because we have all our higher level terms when I stick in the bits for them, those terms are going to be falling down one level each time, and hopefully they'll cancel with these. But the question is there enough weight to cancel with these? So we need, so how much weight can come from level k? So how much weight from the kth level, I'm going to speed up a little, level k can come down and kill this? Well, the total weight at the kth level was Ek, the energy spectrum at k. How much of it can come all the way down to the first level? At level k, you've got a monomial of size k. To bring it down to the bottom level, you have to have looked at k minus one of those bits. Each bit is looked at with probability delta. Things were independent. You would bring it down to the first level with the probability of delta to the k. And so basically, the amount of cancellation from the kth level is e to the k delta k. And the total weight of this has to be able to cancel what remained. But what remained was most of the weight, because you removed very few things. So you end up needing some equation like this. But the EKs add up to 1, and you see that E1 is most delta, or 2 delta. OK, that's the heuristic. Of course, it's far from a proof for a number of reasons. Of course, the main one I said is I assumed in a given monomial that the different bits were probed with the same probability. Independently. And this is not true. OK. So let me now let me give you a proof of this theorem. So we're going to let G be the sum, simply the Fourier series at level k. This is just the sum of the Fourier coefficients at size k. And you will note that the L2 norm of G, that's the sum of these Fourier coefficients, that is precisely the left-hand side of the theorem. We're trying to get a bound on this piece here. And that's exactly, that piece there is exactly the L2 norm of G. OK, so note this is the left-hand side. And, well, I have a delta f on the right side, so let me fix. I want to fix an algorithm A such that delta f equals delta A. You always can find an algorithm A which is minimal. There's not finitely many. I'm doing randomization, but it's sort of a compact situation. So I take an algorithm which is best possible. And this algorithm gives rise, as before, to my subset J of random bits. And now I want to define the following. If you give me any mapping, any function, h, from omega n into r, I want to define h sub j. J is a random function, and I really mean a random function. I don't mean we call random variables, but we shouldn't call them random variables because a random variable, as we know, is a fixed function on a probability space. But we've been caught in this trap of calling it random. But this is a random function in the way you should mean. This function I'm going to describe is random, and basically it's obtained by filling filling in and fixing the bits in J and then using the function h. Okay, let me try to describe this. If you're confused, I'm sure you're not alone. So here's sort of the idea. So let's say in this particular case, when we ran the algorithm, the set J was omega, the first, third, and last bit. And that was the set J. So after we know those bits, we know the function h. Okay? In that case, what I do, and let's say they turned out to be 1, -1, and 1. So now what I can do is I think of those bits as completely fixed, and I obtain a new function which I call h sub j, which is simply it's really a function just of those other variables. And what I do, the way it's defined is whatever I set those other variables to be, I plug them in, and then I just take h of the entire sequence. So after the algorithm's done, I flip those bits, and then I simply take my original function h, and when I stick in the values here, I evaluate it at h. Perhaps another way of thinking about it is in this picture. So imagine here we're thinking of the Fourier representation of f. Imagine instead I had written out the Fourier representation of h. H is an arbitrary function, and I write out its Fourier representation. I then run my algorithm, and it asks for different bits, and I fill in the different bits. And then at some point, the algorithm stops, because I know the function f. H is a different function. H is an arbitrary function. F is the function I'm trying to figure out what it is. So if I take a different function h, write out its Fourier representation, run the algorithm, I start filling these bits. At some point, when I stop and I know f, it doesn't mean I know the function h. So the function h might still have lots of monomials in it. And it's the function that I have at the end, after I run the algorithm, that Fourier representation is that's exactly what h sub j is. Finally, just to make it, since it can be confusing, I'll actually write it down slightly more rigorously. So So in our model, we have two types of randomness. We have omega, which is our sequence of bits. But we also have randomness, which is running the algorithm. And this is going to be denoted by tau. So this is our random element of omega n. This is our randomness to run the algorithm. And so when I put both these sources of randomness together, I denote that by omega tilde. And now I have to tell you, I told you hj is going to be a random function. So this function is going to depend upon what omega is and what tau is. And what it is, its value, so to describe the function, I have to tell you what it is at some point omega prime. And basically what this is this is h of omega double prime where omega double prime is taken to be the original sequence on J, and J depends on both sources of randomness, and it's equal to omega prime on the rest. So this is a more formal way of writing out what I just said. So you fix the bits in J to be omega, the original bits, and then it just becomes truly a function of the other bits. Okay. What I want is, when the algorithm is over, I have a certain amount of information. The information I have at the end of the algorithm is which points I've probed and the values at the points I probed. And so this sigma field I'll call F. It's the information I've obtained during by the end of the algorithmic procedure. And now, if I have any function h at all, then I claim we have this set of equality. Okay. This thing is always true for any function at all. The empty Fourier coefficient is always the mean. Why is this the same? So I want to know the conditional expectation of h given the information I have. So I know the bits in J, and I know their values. So that's why it's reasonable to look at hj, which is simply the same function, but where you fix those bits in J to be what they turned out to be. And this is true basically because of the IID structure. Given the fact that I know the values of the bits in J gives you no information about the other bits. And so the way to compute the expected value is just to take the usual average. So one has this. And so in particular, if you want to compute the expected value of h, I can compute instead the expected value of this quantity here, which is random. And similarly, you can do this not only with h, but you can, in fact, the same type of argument works if you're looking at other type of moments, hj squared, if you think about it a bit. Okay, so that's sort of the setup. So now let's start on the inequalities. Okay, so we have the second norm of g squared. That's the right-hand side, and I want to get an upper bound on that. Well, that's the same as the expected value of g times f. Okay, g is a projection of f. I have f, and g is a projection onto the level k Fourier coefficients. So in order to figure out the L2 norm of g, I can just as well take the inner product of g with the function f. And now I can condition on this information I have from the algorithm, and then I can pull out the value of f. The point is, when you know the algorithm, at the end of the algorithm, you know what the function f is. So f is measured with respect to the sigma field, because at the end of the algorithm, you know what the function is. So I can pull f outside the expected value, outside the conditional expected value, and now I can use Cauchy-Schwarz. And this is at most f squared to the 1/2 times this thing here, this conditional expected value, is the same as the empty Fourier coefficient at j. That's simply this thing applied to the function g, this thing squared, all to the 1/2 power. And basically, the argument is this term is sort of on the right-hand side. Basically, we need a way to analyze that. Okay, so we have the following term. So this is something I want to analyze. I want to compute its expected value. But let me first evaluate this as a random before taking the expected value. So this is simply the level 0 Fourier coefficient, for Gj. So I can express that as I can for any function, is the L2 norm of G, J, and then I subtract all the other Fourier coefficients. And then this, and now at this point, I want to take expected, I can take expected value on both sides of this. And this term here becomes the same as the second moment of G. That's basically one of the general facts I had at the bottom, where we have the expected value of h squared as something. So we end up getting that. And then I have this term here. And so and then I can express, G is simply the sum of the level k Fourier coefficients. So this thing here, I can write, let me write what I end up getting in the end. Okay, so here I have a sum over all the sets bigger than 1. I'll only make it bigger if I just sum over the s's of size k. And these terms here exactly sum up to this. So this corresponds to this. And these terms correspond to that, but only the subset of k. And so I can express this upper bound as this. I'm sorry. Here? Yeah, this is a less than or equal to. Yeah, exactly, because I gave up the terms here. And so now the basic observation is this term is going to be exactly this term, assuming the random set doesn't touch S. So the picture of this is G has all its Fourier coefficients at level k. We have So this is a K monomial, that's a K monomial, etc. And so if we look at a particular one, this one, S, what's going to happen is if the random set J doesn't touch this set, then it's going to remain intact, and so that Fourier coefficient will be what it was originally. And the point is, you might wonder, well, how do I know things higher up cannot come down and kill you? And the answer is they can't, because this function g has all its Fourier coefficients only at level k. There's nothing higher. So basically, nothing can come from above. So if you don't hit j, you remain the same Fourier coefficient. And if it happens to hit you, that Fourier coefficient falls down one level, and it becomes 0. Okay, once you have that, you can bound this thing. This thing here simply becomes, this term here is g hat of s squared times the probability that s intersects j. Because if it doesn't intersect j, then these terms are the same, and they disappear. And on the other hand, if it does intersect it, this term vanishes, and you're left with this. So this particular term becomes at most this thing, and this, what's the probability j intersects s? Each person in S is hit with probability at most delta. There's k elements in S, and so this is at most delta times k times g hat of s squared. That's before I sum up. And finally, when I sum up over S, I end up getting that this thing is at most delta k times the L2 norm of g. Because if I sum up all of these Fourier coefficients over k, I get exactly the L2 norm of g, and I have this delta k. So I end up getting this inequality. I won't do the rest. We have this. Once you stick that inequality in for here, then using this as at most that, you just move things around and you immediately get the inequality. OK. So that took longer than I had anticipated. So even if the proof might not be clear, I hope the statement is clear. So the statement, again, is if you can somehow manage to find functions with small revealment, you get a bound on the level k Fourier coefficients. OK, so now we're just going to sort of use this thing as a black box. So now we want to apply this to percolation crossings. So what we would like to know is, for the event of percolation crossings, what is the revealment? Can we find good algorithms to determine whether percolation occurs which have small revealment? And how small can we make it? And so the proposition is that if Fn is percolation crossing, of a, well, n by n or a or alpha n by n boxes. Christophe did, it didn't matter. If Fn is percolation crossings for this, then the revealment of Fn is at most 1 over n to the 1/4 plus O of 1 in the triangular lattice case, and it's at most 1 over n to some power on the Z2 case. So in particular, there's two things. So in particular, they go to 0. So once we prove this, the revealments go to 0, and therefore by the corollary, we have noise sensitivity. But more than that, the fact that we have powers up here for these revealments will end up easily showing that we get what we want. The spectrums pass some power, or we have a quantitative noise sensitivity estimate, as Christophe described in his last lecture. Okay, so what is the first attempt? First attempt of this is the following. So first recall, forget about the algorithm, just recall all these interfaces you've been seeing in the percolation course. Okay, we're looking for white crossings. I think Christophe was doing red crossings. I'm going to do white crossings. How do we tell if there's a white crossing from the right to the left side? The way we do it is we can send an interface from here to here. So what I do is I color this thing white. I color this. Can you see this reasonably well, the pink? We have the pink here. And what we do is we run the interface which keeps white on the right side, and maybe I should change to orange. That'll be better. Which has white on the right side and pink and orange on the left. So we have this path which has whites on the right side and orange on the left side. It's always this interface goes right between the hexagons. I'm only describing this in the hexagon case. It runs right between the hexagons, keeping white on the right and orange on the left. Now this thing might certainly bounce off the right-hand side, bounce back out. In fact, according to Vincent's lecture today, it does bounce. The SLE6 is bigger than 4, so this thing will bounce, and it bounces off here for a while, so this interface bounces here and here, but eventually it's either going to hit here. So the question is, does the interface hit there first, or does it hit there first? And that's basically will tell you whether there's a percolation crossing, because if I hit the top first, I have my orange blockade and I can't get across. If the interface hits the left side first, on the top I've got my right crossing. So to know if there's a left to right crossing, I just take this interface, start it here, run it until I hit the top of the bottom. Now that basically describes an algorithm for me. What I do is I start the algorithm here, and I simply keep asking questions so I can keep track of the interface. So now the algorithm asks questions to determine the interface. So right away, I need to know if I'm going to make a right or a left turn. So I look at the first hexagon. Maybe it says I'm orange, so I know the interface goes up. Then I ask the next, as you build up this interface, you run into a new hexagon. You have to ask whether it's orange or white, and you ask the question, and then you continue the interface. So if I run this algorithm until I get to here or here, then I can determine if there's a crossing. Okay, that's my algorithm. Does it have a good revealment? Well, just as Christophe did, when he talked about these exponents, he said, let's first look at the bulk before we look at the interior. So let me look at the bulk inside. So for I in the bulk, so the bulk is far away from the boundary, what is the probability that the bit is revealed, that the algorithm asks for the bit. So this particular one, what's the probability it's asked for? Well, if you ask it, that must mean that the interface ran through it. You're only going to ask it if the interface went through you. So this means this is the same as the probability that I is on the interface. But if you fix this location I, what's the probability you have a white path and an orange path to, say, distance n over 2 away? Well, that's exactly what you just saw in the previous lecture. That's another critical exponent. Which I was not going to compute, but fortunately it was even described for you a moment ago. The probability of this is the probability of the 2 arms event. And this is at most, for the triangular lattice, 1 over n to the 1/4. And that's exactly what Vincent described to you. OK. That takes care of things in the bulk. But as you might notice, this algorithm doesn't have particularly good revealment. Because what did the revealment do? It started here, and it asked for this bit. It always asked for this bit. So the revealment of this algorithm is, in fact, 1. It doesn't work at all for what we want to do, because we always ask the bottom right bit. Since always ask the bottom right bit. But nonetheless, it's sort of pretty good. It gave us low revealment. The points in the bulk were very unlikely. But of course, we can't apply the theorem because of the boundary conditions. So that was the first attempt, and now we want to modify this algorithm so it really works. So that was our first attempt. Now here is the remedy. Pick point on middle right side. So I'm going to pick a random point on the right-hand side, just say between here and here. And then what I do, I'm just going to say this in words. I want to know if there's a left to right crossing from the right to the left side. I do this with 2 subalgorithms. I first look above this point, and I ask, is there a crossing from the top half to the right side, to the left side? I ask that question, and that I do that in exactly the same way. I want to know if there's an interface above this random point, so I run an interface from this point up to here. That's the way I would detect if there's a crossing, and I do that the same way. I run my second part of the algorithm. I take a point. I want to see if there's a crossing from the bottom part to the left side, and again, I run an interface. Since I'm looking below a certain point, I have to reverse the color of red and white, but this is a minor point. So basically, I just have 2 subalgorithms. But this choice of this random point at the beginning is part of my randomized algorithm. I first choose that at random, then I run these interfaces. So since each of these particular points are very unlikely to be picked, you don't have to worry. There's no particular point I always pick, but I pick something randomly. And you can argue. I'm not going to do it here. It's only briefly described in the notes. And this uses some half-plane exponents. Just as Christophe also did, he also used some half-plane exponents to prove the evidence, to prove first these results for Z2. And for the triangle lattice, he had to deal with boundary conditions. And you have to do something similar. But when you do that, you do end up, in fact, exactly proving this result. So what I want to see now is we just want to quickly compute, it's an easy computation, what the Revealment theorem, and which is now erased, and this estimate I have here on the revealment for crossing probabilities, we just want to quickly see what this tells us about the spectrum. So the corollary is going to tell us that all the spectrum sitting above n to the 1/8. So corollary for all epsilon positive, if I sum up all the Fourier coefficients, if I sum up k equals 1 up to n to the 1/8 minus epsilon. So this method, the number it's going to give us is the number 1/8. So if we sum up the weight of the Fourier coefficients up until the size, so this will go to 0. That's the corollary, and it follows, here I have sum over all s of size k. So here I have exactly this is the level k, the spectrum, its size k is this, and this, the claim is this goes to 0, and we just plug things in. So we have the sum from k equals 1 to n to the 1/8 minus epsilon. These things here, the Revealment theorem tells me this is at most delta, the revealment, times k times the L2 norm of f. L2 norm of f is bounded. That's, I don't have to worry about that. I can just put in k times the revealment. And the revealment is, by the theorem we just did, 1 over n to the 1/4 plus O of 1. So this, of course, comes out, and I end up summing k up to here, up to a certain level. That's just the square of what I have up here. So this is at most 1 over n to the 1/4 plus O of 1, and then the sum of the first so many integers is exactly n to the 1/4 minus 2 epsilon. The O of 1 term is going to 0, and so this goes to 0. So we see that all the spectrum is past 1/8. So in terms of our updated spectrum picture, for the triangular lattice, we have maybe something like this. So all the spectrum is past n to the 1/8 and below n to the 3/4. So this is still a factor of 6. So I'll leave the following as an exercise. Things like this will be in the exercises, and Christophe already sort of described how you relate the spectrum to having quantitative noise, sensitivity. But let me just state this corollary in a different way, which is as follows. So full gamma less than 1/8. If the noise we use is 1 over n to the 1/8 power, that's a sufficiently big noise to guarantee the noise sensitivity. So a consequence of the spectrum is exactly this. When you noise by this much, that's enough noising to get asymptotic independence. And as Christophe explained, if you take it smaller than 1 over n to the 3/4, they don't become asymptotically correlated, but rather they become completely correlated. Okay, and we still have this gap here. Okay, so is it possible that we could improve? Is it possible that we could? We found this particular algorithm, which I described for you using the interface, and you could ask, well, maybe that algorithm for determining whether the crossing was not such an intelligent algorithm. Maybe, in fact, there's other smarter algorithms with smaller revealment. So if we can find a smarter algorithm than the one I described with a smaller revealment, then we could, if instead of 1 to the n to the 1/4, I could find one who had revealment 1 over n to the 1/2, that would end up pushing this up to, say, n to the 1/4, and then I'd only be off by a factor of 3 rather than a factor of 6. So natural question is, can we improve the algorithm? So I'll make a number of remarks here. One is there is no known better algorithm. So there's no algorithm which you can provably does better than 1 over n to the 1/4. 2, it is believed there are better algorithms. And simulations support this. So at least David Wilson was involved, and by some other people, for a certain project, some paper on random hex, they wanted to, they simulated an algorithm, which they had, and it did better. But you could not prove this algorithm did better. And the algorithm's sort of interesting. And the algorithm, in fact, you could apply this to any Boolean function. And as far as I know, no one's really looked at different Boolean functions to see how this algorithm works. The algorithm is almost something what you would guess. I have a Boolean function. Which bit should I choose first? Well, take the bit whose influence is largest, the one who's most likely to have an influence on the function. Choose that bit. If it's -1 or 1, I set it. I have a new function. Now my function changes, and then I look at my new function, and I look at the one which has the largest influence for this new function, and I keep going. So this is an algorithm which, when they applied it to percolation crossings, it did better than this. But in fact, as far as I understood, they couldn't prove that the revealment, in fact, even goes to 0 for this particular algorithm, I believe. Anyway, so it's believed there are better algorithms, and the one I just described. 3, there's an interesting, and this is a result from theoretical computer science, there's a theoretical result that gives us a bound on how much we can hope to improve. So we have an algorithm of n to the 1/4. You might ask, how small of a revealment could I get? And there's a theorem, which I probably will describe next time, which gives us a lower bound on percolation crossings, which is 1 over n to the 1/2, plus little o of 1. So in fact, we can improve our algorithm by a power factor of 2. Notice that if, in fact, you were lucky, you could even find an algorithm with as small as a revealment as what this theorem tells you. As I said before, that would end up lifting the 1/4, this 1/8 to 1/4, and you'd still be off by a factor of 3 of the n to the 3/4, which is reasonable to conjecture that's where the spectrum is, because we know on average this spectrum is sitting here, so it would be natural to hope and think the spectrum sits there. Okay, so what I want to do now is I want to describe this theorem of O'Donnell and Cervetio. So let me describe this theorem of O'Donnell and Cervetio. Theorem so I need to give a couple definitions. So definition, if I have a random algorithm A, C of A, which is called the cost of A, this is the expected number of questions asked. Expected number of questions asked. J is exactly the random bits I look at. So the expected value, so this is the expected number of questions asked. And their theorem says the following. If f is a monotone function, if f is a monotone function, then for any algorithm A, for f, the cost of A is at least the total influence, which I think of f squared. So the cost is always the total influence square. And as a consequence, this tells us that n times the revealment of f is bigger than or equal to the total influence squared. So the reason for this, it's clear the total cost is at least n times delta f. Because the expected cost, C of A, is simply I sum over all the bits of the probability that that bit is asked for. There's n bits. And this is the maximum probability that a particular bit is fixed, is probed. And so this inequality immediately gives us that. Let me just, next time I'll be continuing a little bit more on random algorithms starting from this point. So let me make a couple more remarks, and then I'll be finishing. So let me first explain why this inequality is much easier. This is a much stronger inequality than that, but let me convince you why this is, in fact, extremely simple. This is true since the event that I is pivotal is contained in the set that I is in J. Notice, if you're in a situation where a particular bit is pivotal, then any algorithm that you run is going to have to ask that bit. Because if the bit's pivotal, if the algorithm doesn't ask what you are, if the algorithm asks all the bits, it still can't determine what the function is. That's the definition for I being pivotal. So if I is pivotal, it must be in the set probed. And therefore, if I sum over I of these probabilities, the sum over I of these things is that, and the sum over I of these probabilities is exactly that. So this inequality is a triviality, follows from this inequality. This is not hard, but it's an essential strengthening. Next time I'll start off showing what this tells us about percolation. I'll mention an open question there, but let me just end by addressing the question about the converse of one of the results. So we said that if the revealment goes to 0, this implies noise sensitivity. And the question whether the reverse is true. If it's noise sensitive, does the revealment go to 0? Okay, let me first give you an uninteresting counterexample, the parity function. For the parity function, it's the most noise-sensitive one, but of course, delta n is equal to 1 because you have to ask for every bit. How about, that's sort of a trivial counterexample. How about if the function's monotone? If the function is monotone, might one have hope that in a monotone case, maybe noise sensitivity implies these things go to 0? This is true for most of the examples we have in the text that were noise sensitive, that some of the exercises were to prove tribes and iterated majority, or they have revealments going to 0. But for monotone functions, in fact, the converse is not true. And there's a nice example, and this is of clique containment. And this is the main reason the clique containment example, which I'm not going to describe here, it's in the notes and was perhaps discussed in the exercises. This is a nice monotone example, which is noise sensitive, but you can prove, and there's an outline in the text, in the lecture notes, that the revealment doesn't go to 0. The clique containment is more or less just the event you take a random graph on n vertices, each edge there is probably a half or not, and you ask, do I contain a clique of size log base 2 of n? That's the right size that you should try to look at to hope the function's non-degenerate, and you can prove that's noise sensitive, but you can actually prove that the revealment is not going to 0. So that's sort of the main point of that example. OK, so next time I'm going to say a few more, maybe spend 10, 15 minutes more on some related thing with an open question, and then we'll move into this spectral sample.